Worksheet number 17 was a homework last night. We're going to go over 5 of those questions from worksheet number 17, 3, 4, 5, 7, and 8, starting with number 3. It says a ray of light passes from air into water. What's the speed of light in the water? We draw this out. If we want to avoid mixing up what's medium 1 and medium 2 and end up making a mistake as a result of that, then we draw this out. Here's our boundary between the air and the water. This dotted line is called our normal line. It's always drawn, it's an imaginary line that's always drawn at 90 degrees to that boundary. It's going from air into water. So we're saying N1 is 1.00. That's the air. And the water, N2, is 1.33. Now, the ray of light is coming from air into water, so it's going to look like this. Can you tell me whether that light is going to speed up or slow down when it goes from air to water? We're going from a low index to a higher index. The light is going to, the speed that is going to, good. If N goes up, V goes down. And if V goes down, theta goes down as well. So we're going to find that theta 2 is going to be a smaller number than theta 1. We know the speed of light in the air is 3.00 meters per second. So we're going to say V1 is 3.00 times 10 to the 8 meters per second. We're trying to find the speed of light in the water, V2. So let's set this up with Snell's law. We've got 4 parts of Snell's law, but of course we only ever need to use 2 parts of it. We're going to say V1 over V2 in this case is equal to N2 over N1. No thetas, that's good because we avoid trigonometry when we're not looking for the angle. We're going to say 3 times 10 to the 8 divided by V2 equals N2 over N1, 1.33 over 1.00. I always like it when the bottom number, N1, is 1.00 because it makes the math a little bit easier, right? You're dividing by 1. Now, to get V2 by itself, we got to take it up to the top here, and then we're going to take 1.33 down to the bottom. So it ends up being 3 times 10 to the 8 divided by 1.33 equals V2. And when you do the math there, V2 is going to work out to be 2.26 times 10 to the 8 meters per second. We expected that, right? We expected that. Okay, with the index of refraction increased, as the index increases, V goes down and theta goes down. So we got a value of 2.26 times 10 to the 8, seems reasonable. Next question was number 4. It says, when light passes from crown glass into air, it refracts at an angle of 55 degrees. What's the angle at which the light struck the crown glass air boundary? Once again, we're going to draw this out so we don't mix up medium 1 and medium 2. There's our boundary and our normal line. We're going from crown glass into air. Crown glass has an index of refraction of 1.52. So we're going to say N1 is 1.52, and it's going to air. We're going to say N2 is 1.00. Crown glass to air looks like this. Okay, there's our ray of light that's striking the boundary. What's going to happen to the speed of this light as it goes from crown glass to air? Speed up or slow down? N goes down, V goes up. Yeah, V goes up, and therefore theta is going to go up as well. So it's going to bend this way. Theta 1 is going to be smaller than theta 2. Now, we know that theta 2 is 55 degrees. We're solving for the value of theta 1 right here. So let's use a part of Snell's law that has theta in it. Sine theta 1 over sine 55 degrees equals N2 over N1. Right? Not 1.52 over 1, but rather 1 over 1.52. So let's do this on the calculator here. Let's say 1 divided by 1.52. That gives me my right-hand side. Now let's multiply that by sine 55. And now let's take the inverse sine of that. As a second function sine of that, we get a value of 32.6 degrees for that. Is that a reasonable number? Yeah, we expected theta to go up because V went up and N went down. N went down by quite a bit. So we would expect theta to go up by quite a bit. It went from 32 to 55. That's quite a bit. So it seems like a reasonable number there. Okay, if you mix these up, And that's a fairly common mistake. And I guarantee you, if you mix those up and it's a multiple choice question, that option will be there. What you get will be one of your options. But there's a nice little check, right? Okay, you can look at this and say, does it seem reasonable? Should the angle have gone up from 32 to 55? Yes, it should have. Okay? Therefore, you know that you haven't mixed these up. Okay? If it's a reasonable number, you know you haven't mixed these up. Okay? If it's an unreasonable number, like you get an angle of 80 degrees, then you know you have mixed them up, because then theta would be going down as opposed to up. Next question, number 5, says light passes from air in a diamond at an angle of 15 degrees. What's the angle at which the calculate the angle at which the light leaves the air diamond boundary here. From air in a diamond. Air has an index refraction of 1.00. Diamond has an index refraction of 2.42. We're going from air to diamond. What's going to happen here? Is the light going to speed up or slow down when it goes from low to high index? It's going to slow down. And if V goes down, theta is going to go down. So it's going to bend toward the normal line here. Theta 2 is going to be smaller than theta 1. That's what we're looking for, is theta 2. Theta 1 we know is 15 degrees. So if theta 1 is 15 degrees, I don't know what theta 2 is going to be, but it's going to be a pretty small angle, right? Because it has to go down quite dramatically from 15 degrees. Let's say sine theta 1 over sine theta 2 equals n2 over n1. Let's say sine 15 degrees over sine theta 2 equals n2 over n1, 2.42 over 1.00. So now what we got to do is get sine theta 2 up to the top, 2.42 down to the bottom. Looks like this. Sine 15 degrees over 2.42 equals sine theta 2. Technically it's over 1, but of course when we divide by 1, we just end up with sine theta 2. Let's do this one on the calculator up here as well. Let's say sine 15 degrees equals, let's divide it by 2.42 equals, and then let's take the inverse sine of that, or the second function sine of that, to get theta. We end up getting a value of 6.14 degrees. Seems like a reasonable number, right? Seems like a reasonable number. N went up dramatically, V went down dramatically, and theta goes down dramatically. We went from 15 to 6. That's pretty dramatic. So that seems like a pretty reasonable number. And 7, we're shifting gears a little bit with this one, because we want to find the ratio of the speed of light in a vacuum to the speed of light in Ruby. If we look back in our physics thesaurus, ratio is the same meaning as the D word, division, divide, right? So we want to divide. If we want to find the speed of light in a vacuum, which is really that C, right? Speed of light in a vacuum to the speed of light in Ruby. Okay. What's the value of that? You said it. Yeah, that's the index refraction of Ruby, right? N is equal to C over V. So all we have to do there is say N is equal to C over V. It's 3 times 10 to the 8 divided by, oh, sorry, we have to rearrange that, I guess. Three times 10 to the 8 meters per second divided by the index refraction of Ruby, which is 1.54. We end up getting a value, no, something's wrong there. Yeah, sorry, I'm doing way more than I have to do here. I need the ratio of the speed of light in a vacuum, which is 3 times 10 to the 8, to the speed of light in Ruby, which we don't know, but that's okay, because we know N is the ratio, which is 1.54. So that's it. Now, there's another way to do this. There's a couple other ways to do it, actually. Some of you may not have noticed that. That's okay. Okay, that's not actually the way that I thought of this question either. When I thought of this question, I thought, well, look, the speed of light in a vacuum, we'll call it V1. To the speed of light in Ruby, we'll call it V2. I know what this is, but I don't know what this is. That's okay. I know that's equal to N2 over N1. Right? V1 over V2 is equal to N2 over N1. And I know the value of N2 Okay, N2 is 1.54, and the index of refraction in a vacuum is 1.00. So lo and behold, it ends up being 1.54 again. Somebody in the last class came up with an even different method for solving this question. Not sure if anybody did this. They said V1 over V2. We know what this is. It's 3 times 10 to the 8. And then they said, well, we can find V2 by saying N is equal to C over V. So V is equal to C over N. Okay, get the speed of light in Ruby, plug it back into here, divide the two, and lo and behold, we end up with 1.54. That's not a particularly efficient way of doing it, this one, because in the end, all you're doing is ultimately doing a bunch of canceling to get what we got right here, to get Joshua's method, but it works. Okay, doesn't matter if it's the most efficient way or not, as long as it works. Okay, number 8, we're a little bit more limited in what we can do for number 8 because one of our mediums is not a vacuum in this case. We've got crown glass and quartz glass. The only way that I could think to do this one is to say V1 over V2 is equal to N2 over N1. You want to find the ratio of the speeds. That's the same as the ratio of the inverse of the indices of refraction. So let's do that since we know those indices here. Crown glass is 1.47. Quartz glass is 1.52. We get a number that is 0.967. So you want to write these as a ratio truly. It should be 1.54 to 1. And we could say 0.967 to 1. All right, we'd spent some time on Friday talking about total internal reflection. We're going to go a little bit further with that today, but I'm just going to real quickly review what it is. Total internal reflection is that phenomenon that takes place whereby sometimes light that would normally refract into a new medium strikes a boundary at an angle, refracts into a new medium. This time it doesn't refract, rather it reflects. When does that happen? Well, the first thing you got to remember is that it happens only when light goes from a high index to a low index of refraction. It will never happen the other way around. Never. If you're going from air to glass, you will never get total internal reflection taking place. Now, that doesn't mean you can't get some reflection, okay, but that's a different plain reflection off of a mirror or plain reflection off of any surface is different than the phenomenon of total internal reflection, where all of the light reflects off of the surface. Let's take a look at the second one here, because this is the situation in which total internal reflection can occur. Okay, this is going to be theta 1 right here. Theta 1 is a certain value. It's a pretty small value. We know that since n goes down in this case, theta is going to go up. So this is going to be theta 2, right? N is a high number, N1 is a high number, that is, N2 is a small number, so theta 1 is going to be a small number, theta 2 is going to be a big number. That's still no reflection taking place right now, so let's increase my angle of incidence a little bit. If I increase my angle of incidence, then theta 2 will also increase. Now theta 2 is, what, 80 degrees or so? It's getting really, really big right now. If I increase my angle of incidence even more to this point, then my angle of refraction ends up being 90 degrees. It ends up skipping along the boundary between the two surfaces, the glass and the air. If I increase my angle even more, so that theta 1 is even bigger, then we're going to find that all of the light just ends up reflecting off of the boundary as opposed to refracting or skipping along the boundary. The red line is actually the one that's really important here, because we call this our critical angle. That's our angle at which total internal reflection begins to occur. The blue one and the green one are below the critical angle. You get refraction, just like we just solved those questions for in our homework on worksheet number 17. If we're at the red line, then reflection begins to occur. If we're above the angle of the red line, then reflection will occur always, not refraction. Make sense? So critical angle is that angle at which reflection begins to occur. Below that angle, you're going to get refraction. Above that angle, you're going to get total internal reflection. We wrote this down on Friday. This just summarizes what we just said, basically. Remember that we have to go from high index to low index, never the other way around. Okay, never from low to high. You're always going to get refraction then. And of course, the angle has to be high enough. And when is it high enough? Well, when it's above the critical angle. The critical angle is the angle of incidence at which total internal reflection begins to occur. Now, I want to show you a couple of situations where a couple of things that we can explain by total internal reflection. Let's say we've got a little fish in the water here. He's all happy. He's got a happy face there because fish is all happy. Along the bottom of the pond, nobody fishing. All of a sudden, somebody's standing over here looking in the water. Hey, guess what? Guy sees the fish in the water, right? Look, there's a fish. Points to his kid. Hey, there's a fish. Look at the fish swimming around. But he doesn't see the fish where it really is. Okay, you guys know that when you look in water, your perception is off. And it's off because of refraction taking place. Let's look at that a little bit closer here. There's millions of rays of light coming from the sun and going into this water at any given time. Okay, there's millions of rays of light, in fact, reflecting off of this fish. Let's look at one ray of light reflecting off of this fish. The one ray of light that reflects off of this fish that I'm concerned with right now is this one. This ray of light reflects off of the fish, and then when it gets to the boundary between the water and the air, it refracts. We know that water has an index of refraction of about 1.33, and air is about 1.00. So as we go from high to low index of refraction, the speed will increase, and the angle will therefore increase as well. Therefore, that ray of light that reflected off of the fish is going to refract like this. It's going to bend away from the normal line and go right into my eyes as I'm looking at this fish. Now, what do I see? I see this ray of light coming from the fish, but my brain isn't smart enough to perceive the ray of light the way that it really traveled. My brain thinks that that ray of light has always traveled in a straight line. So I perceive the fish to be right there. I perceive the fish to be shallower in the water and further back in the water. Right? My brain thinks that that light that goes into my eyes has always traveled in a straight line. So it extends it back to a straight line. Well, then the fish has got to be not quite as deep, and it's got to be further back. Does that make sense? That's not total internal reflection, right? But that's refraction. But watch what happens now when the guy that's looking at this fish steps back a little bit. Steps back right here. Now this ray of light that reflected off of that fish and refracted off of the boundary between the water and the air skips right over my head. Now I don't see it. So I don't see the fish here anymore. Right? The ray of light's still going there, but I don't see the fish there anymore because that ray of light never strikes my eyes. So what we need here now is another ray of light that's coming off of this fish to refract into my eyes. How about this one? Make sense? There's millions of rays of light. I picked one of them that refracted into my eyes. Great, I saw the fish. Now I'm picking another one. Here's the problem though. What do you notice about this theta 1 versus this theta 1? What do you notice about the red one versus the blue one? Yep. Yeah, the red theta 1 is bigger. Okay, the ray of light that would refract into my eyes with the red one requires a bigger angle of incidence. That's fine. Okay, that's fine. We could extend this back and we could see the fish in a slightly different spot, right? But what if I've stepped far enough back that theta 1 for the red one actually exceeds the critical angle? So what if theta 1 is bigger than the critical angle? Then that ray of light that would refract into my eyes doesn't refract into my eyes, it reflects. Does that make sense? What do I see? I see the surface of the water. You ever notice that? Yeah, I don't know if you're like me, but when you go golfing, probably my most valuable thing in my golf bag is my ball retriever. Every time there's water within 100 yards, well, actually that's probably not quite true. Every time there's water within about 200 yards, I seem to be able to find it very, very well. Okay, what they should do is put the green where the water is because I hit it every time. And then maybe I should pretend the green is the water. Um, you put the golf ball in the water, and then you go look for it, and you see it. Okay, and you put your retriever in there, and you put your retriever in there, and sometimes it's a little bit hard to actually get the ball because it's not where it actually seems to be. But you ever notice when you're not right beside the pond, you step back for a little bit, you can't actually see the ball, or even the bottom of the pond for that matter, right? All you see is the surface. That's why when you stand back, all you see is the surface. Where would I have to be? Where would I have to be in order to see the fish from this red line? If I want to see the fish from this red ray of light, where would I have to be? In the water. It'd be a little bit awkward, but I'd have to be in the water right there. Now, where would I see the fish? I could see the fish now. Where would I see it? Well, my brain thinks that the light has always traveled in a straight line, so I would see the fish up here. Now, it's not quite as wacky as it seems because the fish wouldn't appear to be in the air. Remember that if I'm perceiving the fish up there, I'm going to perceive the water to be up there as well, right? So I'm looking up, it's going to look like the pond is above me, if that makes sense. So the fish is still in the pond. I could see the bottom of the pond up there. I could see the water up there. Everything would be up there. Be a little bit confusing, right? Because you look around you and you see water everywhere. If you're looking at the right angle, that is, right? If you're looking straight up, it's no problem. But if you're looking at the right angle, then it would appear that water was above you and below you. Yep. Yes. Yeah. If I was right here in the water and turned and looked directly at the fish, there would be no issue with perception of where it is at all because now the light hasn't refracted, right? Now the light would just be coming straight from the fish right to my eyes. Right? That makes sense? So we've got refraction taking place, and then we've got total internal reflection taking place, and then we've got this wacky thing as well with thinking the fish is above you as opposed to below you. Anybody lifeguard at the pool in Okotoks? Now, it always seems like we have somebody that lifeguards at the pool in Okotoks. One of the things that you have to do in the training for lifeguarding in Okotoks is to lift this big heavy weight off the bottom of the pool, off the deep end of the pool. It's a pretty deep pool. If you look up from the bottom of the pool at the right angle, you're going to see the bottom of the pool. You look up, but you see the bottom of the pool. It's for this reason, right? You look up, you see the bottom of the pool. The time that you won't see the bottom of the pool is when you look pretty much straight up, right? Because then the angle is such that the light's not going to reflect off of the surface. Right? Another one. What a lesson for the guys when you go to buy a diamond ring for somebody in another 10 years or so. And for girls when somebody buys you a diamond ring in 10 years or so. Diamonds are valuable for a number of reasons. They're rare, right? But there's also some specific properties, Kenway, of diamonds that makes them pretty valuable. One of them is the color. Usually diamonds are not colored, right? But if you get a diamond that is colored, and that happens, then they can be particularly valuable. The carats, the size of the diamond, they call it the 4 C's. The color, the carats, the size of the diamond. Okay, the clarity of the diamond. Okay, is it foggy or is it clear? And we want clear, obviously, not foggy. And the fourth one is the cut. And the cut is often overlooked. The cut has to be just right. Okay, this is a cross section of a diamond that's cut just right. Now, from above, you could be circular or oval, square, doesn't really matter. But the cross section of the diamond, you would want to look like this. The reason is because we want diamonds to sparkle. Okay, that's what sets them apart from, let's say, glass. Besides their hardness, right? Okay, that's what sets them apart from something like glass. We want them to sparkle. So how do we get them to sparkle? Well, we cut it just right. When light comes into the diamond, it usually comes from above, right? Okay, you hold your hand out there, the ring's right there, the diamond's the light usually comes from above, just like this. So let's draw a ray of light coming from above into the diamond. Now it's going to strike that boundary between the diamond and the air right here. This is our normal line. Now, diamond has a really, really high index of refraction. And because of that, the critical angle of diamond is going to be quite low. Lower than it is for glass, lower than it is for cubic zirconium, which is kind of the fake diamond. Okay, it's a lower critical angle than it is for anything else that I know of because the index of refraction is higher. That means that this angle, it's not a very big angle, but because the critical angle is so small, what we might get is that angle being bigger than the critical angle. And if that's the case, it's going to reflect right here. Now, if this is something other than diamond with a lower index of refraction, then we're going to get a critical angle that's higher, which means we have less chance of theta 1 being bigger than the critical angle. What might happen if this is glass is that this ray of light that strikes it at this angle right here ends up refracting out. Okay. Why is that a big deal that it reflects? Well, because we see a sparkle when light reflects. Okay, if light bounces off the boundary there between the diamond and the air, it sparkles. Okay, and that's what we want diamonds to do. We want them to sparkle, right? If it refracts, we're going to see the boundary between the diamond and the air. Okay, we're going to see that boundary, but it's not going to sparkle. Okay, that's what we want is sparkle. Now, goes to the other side. What happens here? Well, if the angle is right, then theta 1 right here is going to be the same as theta 1 was over here. So what's going to happen to it? It's going to reflect again. What are we going to see? A sparkle right here. Remember that if it has a lower index of refraction, the critical angle will be higher. You might still get some reflection taking place inside, but you're going to get less reflection taking place inside because you have to have a bigger angle in order to exceed the critical angle. All right? Now the cut's important as well because you can imagine if I cut it differently, like let's say like this, okay, the extreme carat version of a diamond, carat as in like the kind you pull out of the ground, carat version of a diamond. Okay, light goes in right here. Oh, look. Oh, that should be better, right? Because we've way exceeded the critical angle right here, right? Like it's way bigger than the critical angle. What do you see right here? A sparkle. But where does it reflect? Well, it reflects down here. Uh-oh, we're not bigger than the critical angle. So what's going to happen? It's going to refract out. Well, we got one reflection, one sparkle, but when it was cut properly, we had two sparkles. 2 for 1, 2 for the price of 1. Right? If it's cut wrong the other way, again, drawn to the extreme here, like this, short and stubby, light comes in like this. Okay, well, there's my normal line right there. Well, even though there's a critical angle for diamond is pretty small, it's probably not that small. So what's going to happen is it's just going to refract out there. What are you going to see? The boundary between the diamond and the air, but no sparkle. So, girls, if in a while somebody comes and gives you a diamond ring and it doesn't sparkle very much, okay, you need to make a point of explaining to the man who wants to marry you that he either needs to go back and take a little physics so he can learn how to buy a good diamond ring, or not be so cheap. Okay, because maybe he's just trying to be a little cheap. Got a sale on a diamond that wasn't cut very well. Refraction, and again, total internal reflection when the angle is bigger than the critical angle. Yep. Okay, good question. So there's only 2 sparkles, so why do we see the whole thing kind of going crazy? Anybody answer that? Yeah, because we don't just have one ray of light coming in, right? We have millions of rays of light coming in, so we're going to get sparkling like crazy, right? Yep. Not necessarily. No, not necessarily. It's designed such that you're going to get, like, these angles maximize the amount of reflection that you're going to take place, right? But you turn your hand a little bit, like all bets are off, right? But even the edges, though, even the edges are angled in such a way as to try to maximize that. But yeah, you would notice, if you had a big diamond, you'd notice that, if you turn your hand a little bit, you'll get differing amounts of sparkling. But because the critical angle is smaller for diamond, you'll still, no matter how you have your hand oriented, you'll still get more reflection taking place with diamond than you will for anything else. Okay, you might get less if you turn your hand, but you'll get more than you would if you turned your hand and you had glass in your hand. Well, oh, good question. What would happen if you looked at a diamond with polarized glasses? Yeah, it depends on how it's polarized, but yeah, I think you definitely see less sparkle. I'm not sure that it would completely cut it out, but I think you definitely see less sparkle. Um, yeah. All right. So whether we got water, a pond looking for a fish, or whether we got whether we got a diamond and we're looking for the critical angle in the diamond or whatever. How do we find that critical angle? Well, I'll remind you that when you're finding the critical angle, you first of all got to be going from a high index of refraction to a low index of refraction. If we're going from, says critical angle for water, we have to assume that the second medium is air. Okay, we have to be going from water to air, because water has an index refraction of 1.33 and air has an index refraction of 1.00. If we're going the other way around, this wouldn't work. Now, it may be a little weird here to have water sitting on top of air. Perhaps we should have drawn it the other way around and drawn our light going from the bottom. It doesn't really matter though, right? As long as H2O, the water, is our first medium. Okay, that ray of light is coming from the water to the air. We're going to call this theta 1, or actually let's rename it theta C, the critical angle. When we are above the critical angle, we get reflection. When we're below, we get refraction. What happens when we're at the critical angle? Where does the light go? Yeah, yep, parallel to the boundary or perpendicular to the normal line, 90 degrees to the normal line. Good. What's theta 2 equal to there? 90 degrees. Listen carefully to what I'm about to say. When you're solving for the critical angle, when you're looking for theta C, theta 2 will always, 100% of the time, be 90 degrees. Got it? When you're looking for the critical angle, theta 2 will be 90 degrees. So we're going to say sine theta 1 over sine theta 2 equals N2 over N1. We're going to replace theta 1 with theta C. What's sine 90? It's 1. So that's good news, right? Every single time you're looking for the critical angle, the denominator there will be 1. In fact, because it's always 1, we often just leave off the theta 2. N2 over N1, that's going to be 1.00 over 1.33. Please don't get the N1 and N2 mixed up. But if you do, there's an out this time. There isn't usually, but this time there is. Okay, let's solve this, and then we'll take a look at what would happen if you mixed up N2 and N1 here. Sine 90 is 1, so let's just say 1 divided by 1.33 gives me a value of 0.75. Let's take the inverse sine of that. We end up getting 48.8 degrees. By the way, that's the critical angle for water. The critical angle for diamond is something like 24 degrees. I can't remember the exact number, but something like 24. So clearly you can see if the critical angle is that much smaller, it's way easier to get light reflecting when you only have to exceed 24 than when you have to exceed 48 degrees or 49 degrees. Not that I know of. Yeah, not that I know of. Why is it going from water into air? First of all, we have to assume that the second medium, the other medium, is air here. Okay, it could be. I mean, you could have water and glass, let's say, but if it doesn't specify, then we're going to assume that it's air. Now, why is it going from water to air though, as opposed to air to water? Because if the light goes from air to water, where n is 1.00 to 1.33, what's going to happen? The ray of light is going to come in like this, and then instead of bending away from the normal line, it's going to bend toward the normal line. Theta 2 will always, in this case, be smaller than theta 1. We need theta 2 to be bigger than theta 1 if it's going to reflect. So in order to make that happen, it's always got to be going from high to low index of refraction. So if you accept that the two media here are water and air, then we have to be going from water to air, not air to water. When we look back at that diamond again here, when light reflected, it wasn't reflecting off of the air diamond boundary, it was reflecting off of the diamond air boundary, right? Going from high index to low index. Make sense? Again, not the other way around. Good? Now, real quickly here, let's look at what would happen. I'm going to do this in purple because you have to understand that it's not actually correct here, what I'm about to do here, okay? So don't even write this down. Sine theta c over sine 90. Let's say we got the ends mixed up here and went 1.33 over 1. Try that on your calculator and see what would happen. 1.33 over 1 is 1.33, of course. Let's take the inverse sine of that. What do you get? This doesn't happen with normal Snell's law, but for critical angle problems, if you mix up n, it'll give you an error. So you never have to panic about that for critical angle problems. With normal Snell's law problems, you do have to worry about that. But here, if you make a mistake, the only thing you're wasting is your time as opposed to a correct answer, because you'll spot that you made a mistake. All right? Yeah, go ahead. No. There's no critical angle for this at all. Total internal reflection cannot happen here. Okay, even if I made no. Even if I made the angle of incidence gigantic here, like 89.9 degrees, what would happen? Theta 2 would still be smaller than theta 1, and it would get pretty close to the boundary there, but it would never actually get to the boundary there. So there's no critical angle there. There's not even an analogy to critical angle there. This way, you mean? Oh, okay. So here, it's getting a little messy now, so let's just redraw that. So what if I made the angle smaller? There's still no analogy to critical angle there, but let's draw it out just to show you what happens here. So we make the angle way smaller here. It's a tiny angle now, right? What happens? I'm having a hard time even drawing this, but we just find theta 2 is still smaller than theta 1. It's hard to draw because I made theta 1 so small, but right? All right, I want you to take a look at the rest of the worksheet here, questions 9 to 11 on worksheet number 17. You have a few minutes to work with those at your desks.